This question over here is not that bad. Okay, we done in our homework or in the lecture, which is worse than this. Okay, so a rigid L is supported by a 12mm diameter pin at D and 2 millimeters diameter cable at point B and point C. Both cables have a length of 1 meter or 1000 millimeters and are made of steel. We have used strength 400 megapascal and elastic modulus of 200. The L link is located with the concentrated load at E as shown. Okay, the first thing I want you to take note. Okay, I have a question number 8. Tanran Preet, I'm going to do this question. Okay, it depends on how much time it takes. Okay, so I'm not seeing question number 3 yet. Okay, maybe you can ask me later on specifically what issues you have on question number 3, but I'm going to focus on this one first. Okay, so you can see that this structure, a big thing to take note is the word rigid. Okay, you have the word. So I told you guys what it means by rigid, right? When it's rigid, means the deformation is linear. Okay, you will not get any curve at all. This is to simplify our calculation. So from here, let's calculate what we have now. I think this is very good that you all see how I do it, because I have no answer down here. Okay, I'm working as in this is the first time I'm seeing it. Okay, so I want you all to like watch how I consolidate the data. Okay, so immediately we know that the length or the area of cable B. Okay, so area of B is equal to area of C in terms of the cable. So it's equal to pi multiplied by 1.5 times 10 to the power minus 3 squared. Okay. So why 1.5? Because 3 millimeters. 1.5 power minus 3 squared times by shift pi is equal to 7.068 or 69 times 10 to the power minus 6 meters squared. I'll do it again. Okay, 1.5 power minus 3 squared. Shift pi 7.069 times 10 to the power minus 6. So we are okay. Then we have the length of the cable at B is equal to the length of the cable at C. And this we know that is 1 meter. So all these are given. Then we know the Young's modulus is equal to 200 times 10 to the power 9 Pascal. Okay. Next, we are going to construct the free body diagram. Okay, the free body diagram. Okay, and it's going to be a multi-body free body diagram. Okay, so at point E over here, we know that there's a force coming down at 800 Newton. Okay, and then we have point A, we have point B, we have point C, and we have point D. Okay, so point D, we realize that it's a pin. So this is your dy. And I'm just assuming that this is my dx. Okay. And then when we, as I said, before we do, we have to construct our transformation. Okay. And then we have cable at point B and a cable at point C. Okay, so this is our point B over here. This is point C. Now, question for you all. Cable at point B and point C, will it be in tensile compression? Anyone? Yeah, tensile. So this is your tension. And you apply Newton's third law, action equal reaction, this will be coming back. So this is your FB. This will be your FC. Okay. So now you have your multi-body free body diagram done. Okay. So now we have to find FB and FC. Okay. So the first thing we'll do, we're going to take summation about moment in the Z direction at point D. We're going to take moment about point D. The whole thing is equal to 0. Okay, we're going to take moment at point D over here where I'm drawing the dot. So the 800 will do anti-clockwise is positive. I do apologize. Okay, so the 800 will induce a clockwise direction. So minus 800 multiplied by 1, right? And then you will have another FC. So FC is going to induce anti-clockwise plus by FC multiplied by 0.8, right? From point D, right? So FC is going in the anti-clockwise direction. FB is also going to do an anti-clockwise direction. And that distance is 800 plus 500 is 1.3 meters. And then everything is equal to 0. Okay. So you have 0.8 FC plus by 1.3 FB, and the whole thing is equal to 800. Okay, this is equation number 1. So you look at it, anything else that you can do. So 800, okay, I'll check again. 800 multiplied by 1, FC is 0.8, okay, 1.3 FB, so 0.8, 1.3. So that is our equation number 1. Then from here, let's complete the entire static analysis. So you have positive that's going up. Summation about forces in the y direction is equal to 0. You have minus 800 plus by dy is equal to 0. So you know that dy is equal to 800 Newton. But this data is useless, yes or no, right? I cannot find, the question asks for what? The forces developed in each cable. It cannot even tell me that value. Then I form another equation. Okay, summation about forces in the x direction is equal to 0. Right, so you have minus FB minus FC plus by dx, and the whole thing is equal to 0. This is our equation number 2. And now you have 2 equation, 3 unknown, absolutely useless for us. Okay, you can say that this is statically indeterminate, yes or no, right? But you don't need to do this. Okay, so for today we learn about statically indeterminate also, but for this problem you don't need to like allow the thing to expand or contract. Okay, you don't need to do that. Okay, why? Because the next thing we're going to do, we're going to calculate, we're going to determine okay the deflection of the cable. Okay, deflection of cable at point B and C. That's all you need to do. Okay, so we're going to do that. Okay, so I'm going to paste the diagram here so I can see. Okay, I can see some dimension. I know to go up and down. So deflection of cable at point B. We know that it's going to be in tensile tension, so plus by FB. The length that we are given is 1 meter. Okay, the cross-sectional area which we have calculated, which is up here, is 7.069. Okay, 7.069. Okay, FL over the Young's modulus is 200. Okay, so you calculate this. So 1 divided by 7.01 divided by 7.069 power minus 6 divided by 200 power 9. So it's equal to 707 positive 0.313 times 10 to the power minus 9 FD. Okay, I'll do it again. 1 divided by 7.069 divided minus 6 divided by 200 power 9. It's equal to 7. Oh, not 7. No, I got this wrong. Do apologize. 1 divided by 7. 1 divided by 7.069 power minus 6 divided by 200 power 9 is equal to 707.314 times 10 to the power minus 9 FE. Okay, let me do it again. 1 divided by 7.069 power minus 6 divided by 200 power 9. Okay. Then if you look at deflection of point C, okay, so it's FC. The rest are the same. The cross-sectional is the same. Right, 200 times 10 to the power 9. Okay. So this is also equal to 707.314 times 10 to the power minus 9 FC. Okay. That does not mean they share the same deflection. Okay, because the force of B is not equal to the force of C. Okay. So next, so now we have how many equations? Okay. So this is our equation number 3. This is equation number 4. Okay. So what we have is we have 4 equations now. Now this equation is useless. Okay. So this cannot help us solve equation number 1 still. Okay. Then the next thing we do is we look at geometric analysis.